And now we'll go over part 2 of 3.06, the problem set 73, titration. The concentration of an unknown acid or base solution can be determined by titration with a base or acid of known concentration. Acid-base titration is a volumetric procedure for determining the amount of acid or base present in a solution. A volumetric procedure is one in which the volumes of the different components are precisely measured. And remember, that's why we use the burette. And like I said, it didn't show it in the pictures, but it measures in milliliters. So here's a picture of an actual burette, and you can see the little lines on here, and you measure how much the starting volume of the liquid changes, and then you open up the stopcock. Yep, that's what it's called, and it drips out. And then you go down and measure to how much is left. So that's what an actual burette looks like. Okay. Acid-base titrations are most commonly used to determine the concentration of an acid or base solution. For example, you could titrate a solution of hydrochloric acid of unknown concentration with a solution of sodium hydroxide of known concentration by adding sodium hydroxide drop by drop. If you know exactly how much of the NaOH solution to add to the HCl solution to completely neutralize it, and you know the initial volume of the hydrochloric acid solution, you can calculate the concentration of the hydrochloric acid solution. All right, remember titration. An acid-base titration is a form of volumetric analysis. When performing a titration, you must know the concentration and chemical formula for the acid or base that is used as the titrant, so the stuff you put in the burette. It is also important to know the formula for the acid and base of the unknown concentration, which is in the flask at the bottom. At the equivalence point of an acid-base titration, the number of moles of hydronium ions originally present is equal to the number of moles of hydroxide ions added. When titrating strong acids and bases, the pH at the equivalence point will be 7, or neutral. Interpret a titration graph. The graph below shows how the pH of a solution of nitric acid, HNO3, changed as sodium hydroxide was added to it drop by drop. Now, sodium hydroxide, you see OH, so you should know automatically, is NaOH a base or an acid? And it is, of course, a base. At what point has the sodium hydroxide completely neutralized the nitric acid? So we have pH versus volume of base added. We have the pH going up on our y-axis. We have the volume of the base added in milliliters across the bottom. Recall definitions. The acid is completely neutralized when all the hydronium ions have reacted with hydroxide ions to produce water. So we have a neutralization. That is, when there is no excess hydronium or hydroxide ions in solution. By definition, this occurs at pH of 7. The pH of 7 was reached when? So let's look at pH of 7. Let's go over to our graph. It hits our line right here. Let's drop down. And that's how we know that a pH of the solution reached 7 when 20 milliliters of base had been added. So that was when the point at which all the acid had been neutralized. After that point, the base was added, caused the pH to increase past 7 because now the solution is, of course, basic. Example 2. Calculate the concentration of an unknown solution. A scientist has a solution of potassium hydroxide of unknown concentration. First of all, is this an acid or a base? Because of the OH, it's a base. She puts 25 milliliters of the potassium hydroxide solution in a flask. She titrates the KOH solution with 0.0100 molar HCl solution. Okay, HCl, is it an acid or a base? It starts with an H, therefore we know it is an acid. It takes 13.6 milliliters of the hydrochloric solution to reach the end point. What was the initial concentration of the KOH solution? Both chemicals dissociate completely. Calculate moles of acid added. So we started out with 13.6 milliliters of HCl. And of course, then we need to change it to moles. Well, they tell us the molarity. Now remember, what does molarity mean? It means moles per liter. So they took this number, I have 0.01 moles per 1 liter. Okay? Then they turned these milliliters into liters, and they did the calculation, and they started out with 1.36 times 10 to the negative 4th moles of HCl. Now calculate the moles of the base present. Every mole of KOH present in the solution will require 1 mole of HCl to neutralize it. Therefore, if the KOH solution required 1.36 times 10 to the negative fourth moles of HCl to neutralize it, there must have been 1.36 times 10 to the negative fourth moles of KOH in the solution to begin with. Okay, how they knew this, how they knew it was a 1-to-1 ratio is over here in the tip. Always write out a chemical equation for the neutralization reaction that takes place during a titration, especially if you are dealing with an acid that has more than one proton. Take that into account in any calculations. For the example here, the neutralization reaction is the one shown below. So we have KOH plus HCl. Okay, and we know it produces water. Okay, so that's where the OH and the H go. What do we have left over? K and Cl. We write the K first because it's positive, so we made KCl. It is balanced, so therefore we have a 1-to-1 mole ratio. And then we can solve. The concentration of the KOH solution is equal to the number of moles of KOH divided by the initial volume of the solution. So we have how many moles we have, divided by the fact that up here it said we have 25 milliliters of it in the flask. So we divide it, we change our milliliters into liters. Why? Because we need moles per liter to get the molar. And our answer is 5.44 times 10 to the negative third molar KOH. All right, problem time. Number 1, sketch a graph of pH against volume of acid added for the titration of a solution of NaOH of unknown concentration with drops of HCl of known concentration. So I'm going to go through these one at a time. So hit the pause button, make your graph. When you're done, hit play again, and I'll go over the answer. And here's the answer. And remember, you always have the answers in your student guides as well. A sample graph is shown below. The curve should start at a high pH because it was a base, decrease slowly at first. So if you started yours at like 13 or 14, that's fine. You're more looking for the pattern. Did you start up here at a high pH? Go down slowly, slowly, and then all of a sudden, boom, decrease rapidly over a short distance. So a nice, very negative slope. Near pH of 7. Okay, right, so we got the 7 right in the middle of our downward here. And then once we got down to it being acid, it's going to decrease slowly. Okay. So really, like I said, if you ended up having it go all the way down to 0 or having it just go to 4, that's fine. The main idea is, did you know that it went slowly, slowly, boom! Include the 7 in the boom. And then once you hit the fact that it was an acid, it went slowly as well. All right, question 2. A sample of 60 milliliter of 0.15 molar HNO3 is titrated with 0.5 molars NaOH. What volume of NaOH is required to reach the equivalence point? Both chemicals dissociate completely in water. Now, if you don't even know how to start, the first thing I want you to do is just write a list of everything you know. Okay, at least start there, and then look at things like, okay, milliliter. Do we want milliliter? No. Okay, change that to liter. We have molar. What does molar stand for? Okay, moles per liter. If you can get farther than that, hit the pause button. If not, go ahead and keep going and listen to me go through the answer. Okay, the other thing that you need to do is you need to make a balanced chemical reaction. So try and do that. Hit pause, and when you're ready, hit play. So we have our chemical reaction. We have HNO3 plus NaOH yields, we know it used water. Okay, so then put together what you have left over. The sodium goes first because it is positive, and then the NO3. If you didn't know the charge of NO3, remember you have that list of polyatomic ions that I gave you and told you to print, and the charge of NO3 is -1. Next, calculate the number of moles of HNO3 initially present in the solution. So if you didn't do that on your own, but you think you can, hit pause and try and do that part. And so we have 60 milliliters of HNO3, but of course we have to change that into liters. And we have the molar. We know that it is 0.15 molar, so 0.15 moles per liter. Put that in your calculator, you get 9 times 10 to the -3 moles of HNO3. The chemical equation shows that 1 mole of NaOH is needed to neutralize each mole of HNO3 because they have a coefficient of 1 when it's balanced. So 9 times 10 to the negative third moles of NaOH are required to reach the equivalence point. Finally, calculate the volume of NaOH solution required to yield the necessary number of moles of NaOH. So if you didn't do it on your own, try it now. Hit pause and hit play when you're ready. And so we have 1 liter of NaOH over 0.5 moles of NaOH times 9 times 10 to the negative third moles of NaOH. Why did I have to put moles on the bottom? I had to put moles on the bottom because I want my final answer to be in liters. Because I want my final answer to be in liters, liters has to end up on the top of my fractions. So instead of doing moles per liter, I did 1 liter on top, put the mole on the bottom. And then the moles canceled. And my answer is 1.8 times 10 to the negative 2 liters, or 18 milliliters of NaOH. All right, and the last one. If 22.4 milliliters of 0.01 molar HCl are required to completely react with 15 milliliters of NaOH, what is the initial molarity of the NaOH solution? All right, I don't like that they use 22.4 because this is not talking about gas, so don't start thinking about the gas laws and that. We're dealing with liquids. It was honestly just stupid they picked the number 22.4. So, all right. So if 22.4 milliliters of 0.01 molar HCl are required to completely react with 15 milliliters of NaOH, what is the initial molarity of the NaOH solution? Hit pause, go ahead and solve it. And of course, the first thing you want to do is a chemical reaction, okay? And if you're having problems with that, when we do a neutralization, what has to be one of the products? Has to be water. So, okay, so pull out the OH and the H. What am I left with? NaCl. So we have our equation, HCl plus NaOH yields table salt plus water. Now calculate the number of moles of HCl added to the NaOH solution. So, here, we'll scrub a little bit there. 22.4 milliliters of HCl, and we're going to times it by the molarity, which is 0.01 moles per liter of HCl. Change it from milliliters to liters, and we get 2.2 times 10 to the negative fourth mole of HCl. The chemical equation shows that 1 mole of HCl is required to react with 1 mole of NaOH. So the original NaOH solution must have contained 2.24 times 10 to the negative fourth moles of NaOH. Finally, calculate the molarity of the initial NaOH solution. And it is 2.24 times 10 to the negative fourth moles of NaOH divided by the fact that there were 15 milliliters when we started. So if we go back up, we started with 15 milliliters. And we change it from milliliters to liters, and we get an answer of 1.49 times 10 to the negative 2 molar, or moles per liter, of NaOH. I would strongly suggest, if you couldn't do these on your own the first time, watch it again, try and do them on your own. If you need help, please do not hesitate to ask. Have a good day.